everyone, it's Judy. Welcome back to this week's Ecosystem Podcast. Today I'm joined by regular guest Steve Sandler. We're going to talk all about probes. Have you ever given much thought to your probes, how they work? Are you getting accurate test and measurement results? Are you really sure? Which way is the signal moving? Why are there so many probes? Why do I have to have a custom probe? We're going to dive into all these subjects from guru Steve Sandler. And we're also going to talk about a bleeding edge probe, probably the first of its kind in the world, that's going to be displayed at the Tektronix booth at DesignCon at the end of January. So we're going to tease that a little bit. And we're also going to talk about some articles he's written that are probably of interest to you. And then we're also going to talk about some presentations he's giving at DesignCon that I thought would be of interest. So without further ado, let's jump right into this conversation with Steve Sandler of Picotest. Hi, Steve. Welcome back. You're one of my favorites. I'm glad you could join today.
Oh, it's always so much fun. So thanks for having me. And talking to you is really easy. So looking forward to this.
Well, you are with Picotest, the company you own. Why don't you first give our audience a little preview about who you are and who Picotest is, and then we're going to dive right into everything about probes.
Sure. So, well, I guess the white beard gives away the fact that I'm old. So I've been in power electronics a very long time, since the 1970s. I've been in power electronics. And my first company was called AEI Systems, and it did simulation and modeling of satellite systems. And I thought I retired in 2000, but I guess it didn't stick. So I ended up with another company called Picotest. And we make test and measurement instruments and probes that help engineers make better measurements. A lot of it's for satellite systems, but also for high-speed stuff.
Well, we were talking recently, and I thought you proposed a really good topic to discuss. And so I want to dig into that because it's kind of going to a fundamental fact of what is a probe. You know, you've taught me a lot over the years about, probes, signal injectors, all this, and I had no idea how complex it was. So I know you were really smart and you could do all the math behind it, but I didn't know just functionally. And I thought that engineers and listeners would really enjoy sort of getting a, probes 101 and really understanding, because I think it's something I'm not the only one that doesn't know about that. So why don't we just start out with, how would you, Steve Sandler, define a probe?
That's a really good question. I could tell you that I knew you were going to ask that question, so I looked it up on Google today. And Merriam-Webster says that it's a device that's used to investigate hidden things. And I don't know if that's really true or not, but I guess maybe it's partially true. But if we look at the way that the electronics world works, we end up with instruments that are on our bench, and then we have the circuits that we're measuring. And so the question is, how do we get those two connected? And so we need to connect the scope to the board somehow. One way we can do that is with coaxial cables, and a lot of engineers do use high-speed cables with SMA connectors or 3.5 millimeter connectors or whatever. But if you want to be able to move it around real easily, it's a lot faster and quicker if you can use a probe. So a probe is a device that makes the connections between the instruments and the board that we're testing. That's the best definition I can give you.
I mean, most people know what a probe looks like and are accustomed to seeing, engineers using probes on a lab bench. But what actually, it kind of goes along with investigating, right? So what actually does the probe do? And then I'd like you to talk about sort of the signal generation and which direction it's going and things like that.
Sure. So the probe's job is to do, I think, two things. One is that it needs to convey the information between the board that we're testing and the instrument, right? And it needs to do that. And it needs to do that with high fidelity. We need to get the information accurately. So we need to accurately get the information between the instrument and the board that we're testing. But there's the second piece, and the second piece is often even harder than the first, and that is that we can't interfere with the processing of the circuit in the meantime, right? So We have to be kind of like this innocent bystander that's able to watch the things going by, but
Hmm.
we're not allowed to change the result. And so that's the things that the probe has to do is it has to convey the information without changing the information, and it needs to do it accurately.
In other words, it needs to be like a good journalist, right? Stay
There you
objective
go.
and not
Exactly.
interfere, not add opinions, just measure.
Exactly.
Gotcha.
Exactly. Just the facts.
Just the facts. Exactly. So you taught me something recently, and I felt kind of silly for not knowing it, quite frankly, but I feel that way a lot. Um, but I've always thought about a probe being a passive device and just measuring it, measuring the signal and what's happening.
Mhm.
But you've taught me that the signal can also be injected. Am I saying the term right? Through the
Sure.
probe. So tell us a little bit about that.
I think you shouldn't feel silly about that because I think most engineers really believe that probes take information from the
Yeah.
circuit and get it to the instrument. And nobody
Yeah.
really thinks about the fact that it's really a bidirectional communication. But if you think about it, for example, a time domain reflectometer, we use those all the time for measuring out printed circuit board coupons, high speed traces and all those things. And most of the time we use a probe to do that. So we connect the probe to the time domain reflectometer at one end, and then we connect the spring pins of the probe to our circuit board at the other end. And what's actually happening, the TDR, the reflectometer, generates a signal. The
Hmm.
signal goes down to the cable, hits the board, measures the board, and of course, the reflections go back through the cable the other way and show up back in the instrument. That's what we measure in the time domain reflectometer. So in that case, we're sending signals through the probe, and we're also receiving signals through the same probe. There are other instruments that do that too. For example, a vector network analyzer, if we make a S11 measurement, a single port impedance measurement, then in that single port impedance measurement, the VNA sends a signal down to the probe, measures the reflections when they come back. We also have two port VNA measurements. And in that case, we have a signal going from one port through the probe to the board, and it's received by the other probe in the vector network analyzer. So we measure the signal going through this thing in one direction. And then the vector network analyzer changes direction. It generates a signal on the second port, goes back through the cable, and measures it on the first. And so we talk about these signals like S21 and S12,
Mm-hmm.
which talks about the direction that the current is flowing. Which way is it flowing through the probe? But in both probes, it's flowing in both directions. We send information and we receive information from the same probe.
And that's all done in a single probe. Like sometimes I see one probe being used and then two probes. And the two probes, I think, is looking for open and shorts. I think. Is that
So,
correct? Or like, what is the difference between a
sort
single
of,
probe and two?
sort of. So, when you think of a single probe, usually we mean that that's a single port. And a
Okay.
single port means that I'm connecting to one connection on the board. So if I'm making a one port impedance measurement, I have one probe.
Okay.
If I go make a two port impedance measurement, well, most of the time we would use two probes,
Okay.
one probe for port one probe for port two, and we would connect those to our DUT ports in order to get the signal. That's not always true either, right? We kind of shook it up a little bit at Picotest and we said, well, it's really hard to hold these two probes at the same time. And we've got
Mm.
to make sure they stay at the right angles and you can't move them. So we took both ports and we put them into a single probe. And so
Okay.
it looks like one probe, but it's actually two probes inside the handle. And that way we can manage the angles and the distances and all of those things. And you'll only got to hold one thing in your hand. So we shook it up a little bit, but that's the way it would generally work. You would generally have two probes to do a two port measurement.
Well, because you and I work together and we're friends and colleagues, you have shown me so many different probes. And why? Why does there have to be so many different types of probes? The way you're talking, like if you need a single port, a double port, TDR, you do this, this, this. It seems like there'd be like 10 probes in the whole world, but there's not.
Yeah. And this is a question I get a lot, not just about probes, but why do we make so many signal injectors?
Yeah.
And so in my lectures, I often say, it's a simple question to ponder. And there are these parallels. Why does my wife need so many shoes? Why does she need so many necklaces? Um, and of course, she responds and says, I was out in your toolbox, and why do you have so many screwdrivers? Why you got so many drill bits? And I would say that it's really just like that. So the probe's job is to make this accurate connection between the instrument and the board. Sometimes it's because they need a special size. I need something that fits between these two pins, and that's not a standard size. Can you make me a probe that can do that? Sometimes it's because there's a really tight space. Can you make a probe that'll fit in there?
Mm.
We have customers that say, could you make a probe that can fit in this automated test system, right? We have this robotic arm that we move around and we want to use that for our probe. Can you make a probe that would fit in this robotic arm? We've been starting to get even more questions from some of our customers. They're measuring their high-speed chips, and these high-speed chips are getting faster. They're getting higher powered, and it's getting really noisy trying to measure near these chips that are generating so much noise. So, for example, we had a customer recently said that asked, can you make a probe that has a filter inside it so that we can block out all those signals except in the band of our phase lock loop? And so we did. We made a custom probe for them that had exactly the size that they have between the balls of their chip. And it had a filter inside the handle so that it blocks out everything from the instrument except for the frequencies that would bother the phase lock loop. And then they can make this great measurement. Sometimes they say, can you give us some special attenuation? Sometimes it's because they just can't find a probe that's quiet enough or that has the bandwidth or, something like that. And so the result is we make an awful lot of probes.
Yeah.
And I think that we're one of very few companies that really enjoys the semi-custom and custom business. Not too many companies do that. We love that. We love the customers that come to us and say, could you make a probe that does that?
You
'Cause
love it. I think that's your wheelhouse, Steve
for
Sandler.
me, that's fun. It's
I
like,
know.
oh, yeah, I think I could do that.
Yeah. So you're saying that it's application driven, it's speed, it's pitch, there's just so many varieties that
Exactly.
it's not a
Exactly.
one size fits all. It's not just like
Exactly.
one Phillips screwdriver and you're good to go.
Yeah, there are things that work on that I'm not allowed to talk about, but that generates a lot of probes too. Things that don't match standard pitches. They're unique, and the probing for them is really precise. And so we make probes for that too. But there's a lot of requirements for custom probes. Interestingly, every oscilloscope ships with scope probes, right? Every channel comes with its own probe, and those probes are almost never usable. And so it's kind of
Really?
interesting because there's this interaction that neither side really likes. The scope companies would love to not have to sell all those probes with the scope, right? Especially the new 8-channel scopes. Man, we got to ship 8 probes with that. That's a lot of money. And then the engineer receives it and says, well, I can't use those probes. Those aren't any good, right? So they don't use them. But the scope company can't stop shipping them because everybody expects it to come with them. So somebody needs to be the one that says, you know what? I don't need the probes. Why don't you keep them?
Right.
But it just doesn't work like that. I wish it did, but it doesn't.
So tell us, you know, stories from I wrote a blog once. It was called like Stories from the Ledge, and I know you're way out on the leading or bleeding edge with a lot of companies you've worked on. What are some of the most sort of unique or perplexing probes? I know you've worked a lot in the space and space applications, but you
Yeah.
also work a lot into like all the big guns on with semiconductors. What were some of your personal, because I know this is your form of both industry but play. Tell us
Yeah.
fun stories of probes you've gotten to work on or develop.
We made an awful lot of them. The first real custom probe we made, we were really surprised because it was NASA that came to us and said they needed a special probe. And we weren't sure what was special about it, but then they told us they had a 120-volt space bus, but they needed to measure noise on it that was in microvolts. And I'm thinking, wow, the noise of a high voltage probe for 120 volts is noisier than that. But they said, is there a way that we can make a probe that can measure microvolts on a 100-volt bus? And of course, I mean, this is my favorite thing. I love this. I'm like, there's got to be a way. There has to be a way. Yeah, so we did. We figured out how to do it, and we made the probe. And for us, that's a lot of fun. We're glad we were able to do it. Of course, we were thrilled that it was for NASA, right? And we don't expect to ever sell that probe again. It's a probe that NASA needed. It's a kind of like a one-shot deal, right?
Mm-hmm.
And then we had Quorvo came in and needed a very similar probe, and they make a 65-volt um, solid state power amplifier. Yeah, and they're also looking for microvolt level noise under 65 volts. And I'm thinking back to how I did that. And I just wrote an article about all the different ways that you can measure, noise on power rails. And power rail probes are really good. Fortunately for me, maybe they only go up to 60 volts. They don't go to 65. And so Quorvo needed a custom probe. So we pulled out that old NASA probe and we reconfigured it, and we made a probe for Quorvo to measure their solid state power amplifier. They were so pleased with it. They actually published an article. I think it might be in Signal Integrity Journal, called "How to Probe High Voltage Power Supplies."
Would you
And
share that with me,
yeah,
Steve?
yeah,
I'm
sure.
sure it'd be fun for our audience to
Sure.
to
It was
geek
written
out
by
on that.
a guy I know a long time, probably more than a decade. He came out of Texas Instruments. His name is Masashi Nagawa. And he's really smart. He's a really great guy. And he knew what the challenge was. And, there's some people that really don't know. It's like, hey,
Right.
can you measure a molecule for me? Um, I don't know where it is, but maybe you could figure it out and measure it. Masashi's not like that. He's really smart. He knew what he was asking for. And if he knew how to do it, he wouldn't have called us. He would have done it. So he knew it was difficult, and he was really thrilled when we pulled it off. But that was another one. Um, we had another customer this year. I don't know if I'm allowed to say who it was, but they wanted to do testing at minus 60 degrees C, and there aren't any probes that can tolerate that. So they asked us if we could use our probes at minus 60 degrees. And I said, I have no idea. Um, go for it. Try it. If you break the probe, we'll replace it. And they did break the probe, but it worked. So they kind of made it a single-use probe while we're off developing a minus 60-degree probe. And we figured out how to do that. It requires some special casting, and probably first quarter of next year we'll have our minus 60-degree cast probe, so people could do really cold temperature testing. But it's almost always something like that somebody has this really unique requirement, and it's really out in left field, and can you do this? And the answer is probably not, but yeah, we're going to pull a rabbit out of a hat somehow. And we do.
So I'm thinking here about our watchers and listeners, and if you could just sort of give some basic advice to maybe not so much the bleeding edge, but people that are working on complex electronics in regards to probe and measurement specifically. I know you have probably forgotten more than most people know. Like, what kind of blind spots do you think are out there, that, or just advice you'd give regarding test and measurement, specifically around the proper use of probes and measurement
Yeah,
techniques?
that's a really good question. And we have an awful lot about that in our online class, but there's really two parts to it. One is noise management, and a lot of the class is dedicated to how you manage noise. And that's one of the things that we really have to worry about in probes, partly because noise penetrates the cable itself, but
Mm.
also where it is that the probe connects to the board. It's very susceptible. They're almost like very small antennas. And so you pick up a lot of noise that way. But most measurements are wrong. I think somebody once said, and I don't know who it was, I wish I did because I'd love to credit it, but he said most measurements are wrong, but some of them are useful.
Oh
And
my.
and it's almost true. Um, the problem is that when you look at the circuit, remember I said you have to do two things. One is you have to get the signal to accurately get between the instrument and the board. And the second one is you need to not influence the measurement. Those two things together turn out to be really difficult. So let's say we have this high speed chip and we want to look at one of the signals from this high speed chip. So we make a probe that can fit on the balls of the package, and we make this measurement. And somebody says, is that measurement correct? And the answer is twofold. The answer is not correct, or it is correct for the measurement that we made. So there's bond wires and stuff that go to the die, and then there's stuff that's hanging on the printed circuit board that's also on that same connection that we made. So I didn't actually see what was at the die, but I
Mm.
did measure what was at the point that I looked at. Now, if I go move the probe to that same signal, but at different points on the printed circuit board, I'm going to get a different answer. So I think that you have to be very specific when you're making this measurement. What is it that I'm trying to measure? What's in the way? And so if you look at the printed circuit board, there's transmission lines and stuff like that, then all of a sudden it starts to make sense. And if you are using a EM simulation tool, what I tell people is make sure that what you simulated and what you measured were at exactly the same point, right? And that'll help
Tricky.
in getting the measurement. Um, Also, I tell engineers that two things you can do. One is you should always measure the impedance at the point that you're going to be measuring so that you can prove that the probe is a higher impedance than that measurement. It's not going to influence it. And that's one thing that you can do. And the second thing I tell people is that um, you need to make a measurement that you know the answer to so that you
Mm.
know that you got the right answer.
Right.
And we have a couple of articles. There's one I wrote for Signal Integrity Journal called Measuring an Oscilloscope Probe Requires Two Channels. And it talks about why it is that almost every measurement that a probe manufacturer makes is wrong, or at least not useful for the measurement that we want to make. And very simply, it's because they use a signal generator that has a 50 ohm source.
Mm-hmm.
That gets rid of all of the overshoots and stuff in the probes. When you measure it without that, it looks really different. And so we make a couple of devices for measuring probes just so we know what the artifacts actually look like. And so those are the guides that I would give you. Measure something that you know and make sure that you didn't influence the measurement. Make sure you understand what's between the point that you connected to and what it was that you wanted to know.
Well, you led me right to an interesting point, something we're discussing recently, because I know you have got a lot going on in DesignCon this year at the end of December. So, for our listeners, the articles that Steve mentioned, I'll go dig them up. Signal Integrity is, as well as Picotest. I'm glad to have them as sponsors of this podcast because of their continuing passion and interest in educating engineers. But I'll link to those resources so you can go dig in there. But when it comes to DesignCon, um, I know that I think you and Heidi Barnes from Keysight, and I'm not sure that Ben Dannon's involved in that one, though I know you guys are writing a paper together. But you're
Yeah,
going
he
to
is.
do a calibration class in Chiphead Theater at the end of January. So can you
Yeah.
talk about what inspired that between you and Heidi?
Yeah, a couple of things really. One is that so many of the support questions that we get are about calibration. What's the difference in calibration and de-embedding? How do you calibrate a two-port probe? What happens if I don't calibrate? How do I know if I need to calibrate? And we were trying to figure out how to best calibrate our own probes. And of course, Heidi's always working with us to help with that. And so we said, you know what? everybody needs to know this stuff. So why don't we just do a session at DesignCon? And we asked Naomi, and she said, "Oh, that'd be awesome. I'll give you guys a table at Chiphead Theater. Have at it." Ben Dannon, I don't think is formally listed on that paper, but he said he wants to help. So Ben will be there, and he'll share what he knows also um, about calibration. And there's going to be a lot going on at DesignCon. There's a lot to see, and that's one of my favorite events, I think, at DesignCon this year. But there's a lot of surprises coming.
Well, give us like a tease of what you're doing. We can talk about it later, maybe. Schedule permitting, we'll see. I'm hoping to have you and Heidi and Ben back to talk about that paper, because I appreciate all three of you so much, and you three working together is an exciting proposition. Um, but just quickly, quick fire, tell us the papers that you're doing, and then give us a tease. I think that you're working with Tektronix on revealing something special at DesignCon. So tell us
Oh yeah,
whatever you can tell us about that.
yeah. Okay, so I'm actually participating in 3 sessions at DesignCon this year. 2 of them are with Heidi Barnes. We're doing a paper with Heidi, Ben Dannon, and Christian Yachts at Texas Instrument. We're really excited about that new edition, and that's on modeling VRM. So maybe I think it's about 37 years ago now, I published my state space average model, which is still in use today, and we finally ported it to ADS back in I think 2015. But engineers really are struggling to understand about state space modeling and how it is that you populate these devices for measurements. And so we put together a tutorial on that using case studies that Ben actually did himself to model a VRM. And we turns out the application guy at Texas Instruments, Christian Yachts, and he said, "Oh, he'd love to participate in this paper since it's his device." And so it's really nice to bring in the semiconductor community too. But we're
Mm-hmm.
going to teach people how the Sandler state space average model works and how it is that we populate that from data. Scott Witcher from AEI Systems, he's giving a paper on Q management, a quantifiable metric for PDN impedance,
Mm.
and specifically using the Sandler NISM tool, which was, my PhD thesis. And so he found a unique use for NISM in quantifying Q of PDN power rails. So I'm a co-author on that one. So those are the 3 events: the calibration event, the VRM tutorial, and this one with Scott Witcher. And yeah, I'll tell you a little bit about
Yeah.
the Tektronix thing. It's really exciting. It took me a couple of years to pull this one off. So I said the probes are bidirectional, and the goal is to get the signals between the instrument and the dot really accurately. So it turns out that measuring transceivers isn't so easy, and this is, kind of a new passion of mine. Is not just PI, but power aware SI. So, how does the power affect the high speed stuff? So the transceiver community, 400G, 800G community, came up with a requirement to test the noise sensitivity of their power rails. Unfortunately, they couldn't find anybody that could actually provide that signal. And so they stumbled across us and said, "Could you make a device that does this?" And it was really interesting. I love these things. Um, but it turned out that we had to meet 2 requirements that were really never done before. One is that we had to put an awful lot of power into the head of our device. And because we needed to get the signal transferred to the dot accurately, it had to be within about 3/8 of an inch of the transceiver. So it made it a probe.
Mm.
But it still had to be a high power device. So the question was, how do you get the heat out of the probe?
Mm-hmm.
And so we made the very first water cooled probe, and we're going to show that at Tektronix booth, hopefully with the high speed transceiver signals running at the other end, so we can see what power aware SI looks like. But it's going to be the first time this probe is shown. It took us a couple of years to figure out how you do a water cooled probe, but we're really excited that we've got it.
That's super fun. I think people would love to geek out over that and just see it. So that's going to be, you said, in the Tektronix booth. And
Will be,
knock
yeah.
on wood, we'll get some measurements out of that puppy by the time they get there, right? And
Oh,
you
I'm
can.
sure. I'm sure hoping, and we will have delivered our first probe to a customer before DesignCon too. So that's kind of exciting. Also, I don't know that we have all the details yet. We are going to give away some books this year at DesignCon again, so we're a little bit excited about that. And we have some fun giveaways that we'll probably give away also at the tech booth. So it's going to be a fun one this year. I'm really excited about it. It's been kind of a long time coming back from COVID. We had DesignCon in April. It was kind of a soft start. So it's going to be really fun to see all my friends there and, people like you. So I'm
I
really,
know.
really
Well,
excited about it.
I'm excited to be there too. And in fact, I'm working with the folks at Informa who put on DesignCon um, to allow me to do podcasting with people like you and Heidi and
That'll be,
others from the DesignCon floor. So we don't have it all locked up yet, but I hope you guys will. Maybe we'll get a camera guy and come over, take a picture of
oh,
your
I hope
probe.
so. That'd be great.
That'd be
Yeah.
really fun.
It is pretty cool to see it. We're really excited about it and we're thrilled we pulled it off. So,
Well, this has been a super fun conversation. Is there anything else that you'd like to share before I let you go, Steve? I know you're a busy guy.
oh, I think that's it for now. And, it's always so much fun talking to you. So I'm glad I got the opportunity today. What I'll tell you is that there's a lot more coming. So stay tuned. The probe that we have coming next year is even a lot bigger than just a water cooled probe. So stay tuned.
You are a crazy man, Steve Sandler, but really fun to hang out with and learn
I hope
from.
I'm still
So
doing crazy stuff. So, I mean, that's my sweet spot is crazy.
I know, I know. That's what I like about you. Well, thanks so much for joining us today and giving our listeners a sneak peek and well as Probes 101. And I'm sure they've really enjoyed learning about it from the master.
Yeah, well, thanks so much. It was a lot of fun. And we'll have a lot of our probes at DesignCon. So if you're there, come on by.
Okay. To our listeners, I've got to backfill all these amazing resources for you, but I will try to connect you to the papers that Steve's offering, maybe the tech booth location, some of the signal integrity journal, everything we've talked about. So make sure you go check out the show notes and remember to like, subscribe, and I hope to see you at DesignCon. So thanks so much for listening and watching. And Steve, thanks so much for joining us today. We'll see you soon, buddy.
Thanks. Have a good one.
We'll see you next week. Until then, remember to always be connected to the ecosystem.